Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to tell you how the fundamental group gives you a Galois action. And the key to this is the lifting property for covers and the notion of deck transformations. So in this video, I want to work in the category of path-connected and locally path-connected spaces. So let's first look at the notion of lifting properties of covers. So the first definition is fairly general. We're just going to have a map P between two pointed spaces, x tilde, x0 tilde, and x0. So the example that I want to keep here, which is the easiest one to draw and gives you a lot of idea about how this theory works out, is from R to S1, where you write R as a spiral and you basically project down. So of course you can think of this S1 topologically as R mod Z, and that's the natural quotient map from R to R mod Z, if you like. Okay, so there's a map, and this one happens to be a cover, although this definition applies more generally. Okay, so what we're going to do, we're going to talk about lifts. So what's a lift? So what we're going to do is we're going to start with some map, a continuous map, F, from some pointed space I, P to x, x0. Okay, so suppose I is just the unit interval and P is one of the endpoints. Then in this case here, you can think of a continuous map there as just some sort of a path, okay, that say, for example, starts at x0. So let's draw something in like that, okay? So maybe we have a path that goes inside here like this, okay? So we have a map from IP into x, this x downstairs. A lift of this continuous map to here is a map which goes up to the x tilde. Okay, so lift to x tilde means you have a map from, instead of going down to the one down the bottom here, x, you go up to x tilde, such that when you compose this map with this map down here, you recover this original down here. Okay, so let's just see what that is in terms of notation here. So that means you want a continuous map from this IP, the same domain here, but now you map it upstairs here to this x tilde, x0 tilde, so that's the upstairs one, such that if you do this one first and map upstairs to this x tilde, x0 tilde, and then apply this P, which brings you back down from x tilde back down to x, okay, so P composed with f tilde, you recover this f, okay, and in that case, that map which goes to the bigger one is called the lift of f. So in this case, there is a lift of this map, and let me just show you how that works. So of course, you'll want since it's a map of pointed spaces, I guess you started here at x0, so you should start at this x0 tilde. And then you want to make sure that as you move along, okay, its projection down to here is this trajectory here. So that gives you something which goes around like that. So it winds down this spiral, one rung, essentially, okay? So this gives you a lift of this loop here, okay? So that's the definition of a loop. And what's really nice is that if you have a cover, so say P from x tilde, x0 tilde to x, x0, if that's a cover, then you can always lift continuous paths. So more precisely, if you have a continuous path F, from 0, 1, 0 to x, x0, then it lifts up to this x tilde, so it lifts from downstairs to upstairs, and it lifts uniquely. There's a unique lift like that. And also, if you have homotopies between two such paths downstairs, they will lift to homotopies upstairs as well. Okay. So I want to just give you a brief explanation as to why this is true, okay, and hopefully you can see from the picture why that ought to be the case. Okay, so here we'll have some x tilde mapping down to x, and it's supposed to be a cover. Suppose you have here x0 tilde, x0. Being a cover means that on an open neighborhood of this point, okay, you can make that small enough so that its pre-image is the disjoint union of things which is homeomorphic to this one by this projection map. Okay, that's what you have. And so let's try to define as much of the path in the lift as you can. Okay, so you know here you've given some sort of path inside x, okay, f, that you want to try to lift to this f tilde up here. And so you start here, and whilst this path, it starts here, so the lifted path will have to start at x0 tilde. And whilst you stay inside this open set, right, because the interval is continuous, so whilst you're moving from there, okay, you have to stay inside this open set, and since it's a homeomorphism, there's only one choice as to what the lift is. Okay, so you can certainly lift whilst you stay inside this open set. And so the question is, well, can you keep extending further out? Well, if you approach the edge here, then what happens? Well, as you approach the edge, I guess you can use continuity to say where you will move to. So suppose you'll end up moving suppose your your f ends up here on the edge, then your left will end up here, okay? And now you can look at this point and try to extend further by the same technique, okay? You say, well, this is a cover, so there exists an open neighborhood of this point here, which is such that its inverse image is the disjoint union of homeomorphic open sets, and it's homeomorphic via this projection. And then you keep extending out and out and out. And then you look at what is the largest interval that you can make this lift. And of course, it's quite easy to see from this procedure that you can extend it all the way out to 1 here. Okay? And that's basically the idea of how to prove it. And the same is true for the homotopies. Okay? So this is a rather nice feature of covers. You can always lift paths. Okay? So this is called the path lifting property for covers. Okay, so now we can look at the notion of trying to find some sort of Galois action of the fundamental group of some pointed space x, x0. Okay, so remember, we're looking in the case of locally path-connected spaces. Okay, and of course the base point here, that will fix what this actual group is, but if you change the base point, of course, they're isomorphic. Okay, so we're going to look at some sort of a cover. We have a cover here. And what we're going to do is we're going to start by picking an element inside this fundamental group. Okay, so how do you get an element of this fundamental group? So what is the fundamental group here? The elements are homotopy equivalence classes of loops based at x0. Okay, so here's a loop based at x0, but we want to look at things which are continuous deformations of that loop as well. So homotopy equivalence classes of that. But let's pick one loop. Okay, let's just pick a particular loop. So I'll call that some sort of continuous function f from 0, 1, that interval, comma 0 to xx0. Okay, so you're not looking at any continuous map, but you'll look at ones where also f of 1 is equal to x0. Okay, so, but in particular, we have this. Okay, and now what can you do? Now you have a loop here, right? And you have a cover, that's this P. So now you can lift this path to the cover. So we're going to lift this to f tilde, and this goes from this pointed unit interval to the cover x tilde, x0 tilde. Okay, so you're going to map it up. So for example, if this was the loop that you had for f here, okay, written as path, then you get this path here like that. So let's have a little think about this path f tilde, which is this lift, okay, this lifted path. Okay, so remember, what does it mean to be a lifted path? That means that if you compose that lift f tilde with a projection, you recover the original. And if you look at, see what happens at the end of this path, f tilde of 1 composed with p. So this is now f, that's f of 1. But remember, this f is a loop. So you come back to the distinguished point, x0. So f of 1 equals x0. Okay, so what is that telling you about this lifted path f tilde of 1, f tilde? F tilde at 1 is such that when you apply p to it, you get x0. So f tilde of 1 is in the inverse image of x0 under the projection map P. Okay, that's what that means. So to sum up what I've done here is, if you're given a loop inside x based at x0, okay, you can lift this as a path now, rather than as a loop, lift it as a path, okay, to x tilde, and then in that x tilde, it's going to produce for me a new element that's inside this x tilde upstairs, and that element is inside the inverse image of x0. So the example here is that we feed in here a loop like this one here. We lift it to get a path like this, and then what we'll get is we'll get an element, this endpoint of this path here. And where's the end point of this path? This endpoint of this path is in the inverse image of this x0 under the projection map. So under the projection map, basically you get things which are spaced apart, essentially by integers, if you like. Okay? So here you get a different endpoint from the distinguished point. Okay? So pictures you should see is you have these loops here, and we're going to associate to it these endpoints of lifts, which is another point in the inverse image of this x0. And so you can ask now, what, as you vary, you change this loop here, how does this this endpoint change? Okay, so that's a good question. Because remember, what we want is, we don't really want to look at just loops inside here, but we want to look at homotopy equivalence classes of loops. So let's suppose, instead of looking at this f, and it's f tilde of 1, this element of this inverse image of x0, you want to do the same thing with a homotopy equivalent loop, g. Okay, so suppose f and g are homotopy equivalent loops at x0, and h is a homotopy equivalence. We can lift these two loops, of course, to the cover as paths. Okay, so f tilde g tilde now gives you these paths upstairs. Okay, and both of them are based at x0. And what we find is that the endpoint of those paths actually, it doesn't change. F tilde of 1 equals g tilde of 1. So this rule going from this loop here to this element of p inverse of x0, okay, is independent of this choice of loop in its homotopy equivalence class. And it's quite easy to prove this, okay? So what we do, we're going to use this part, which I didn't prove for you in the proposition, that homotopies lift. Okay, so we're going to lift this homotopy h to this h tilde. Okay, and that's a homotopy between f tilde and g tilde, so it goes up to x tilde. Okay, so it's a homotopy, so that means that you have a parameter which basically tells you how you go from f tilde to g tilde. We'll make this the second variable. Maybe the variable here will be t, so when at t equals 0, it's going to give you f tilde, and t equals 1 gives you g tilde. Okay, so let's look at this h tilde. Okay, it's a lift of h, so to be a lift of h means that when we apply p to it, you get back h. So let's see what happens when you're looking at the endpoint of the path. Okay, so this 0, 1 is talking about the paths. Okay, so the endpoint will be the 1 here. Okay, so you look at the 1 here, and t is the deformation. T equals 0 gives you f tilde, t equals 1 gives you g tilde. Okay, so this is equal to h of 1t. And what's h of 1t? Well, this is a homotopy between these loops. Okay, so as such, all these loops always have to end at x0. So h of 1 comma t is always x0. So now if you look at this equation from here to here, that means that this h tilde of 1 for anything will always map any t inside the unit interval to the inverse image of x0 under p, p inverse of x0. Okay. And what do you see here? Well, the point is that, remember, this is a cover. This here is a cover, this p is a cover. And so p inverse x0, essentially by definition of the cover, has to be a discrete topological space, and you've got a map from a connected space here to this discrete topological space, okay? And so this has to be constant. So the value when t equals 0, which is basically the endpoint for f tilde, so it's f tilde of 1, that's the same as when you move up to t equals 1 to give you g tilde of 1, okay? So that proves this fact here. And that means that you can make this definition, okay? Okay, the association from f to f tilde 1 doesn't depend on the homotopy equivalence class of this f. So you can take that homotopy equivalence class of f, and you write dot of x0 tilde is going to be defined to be f tilde of 1. Okay, so that gives you an element of p inverse of x0. Okay, so this is essentially our Galois action of the fundamental group on P inverse of x0. There's only one other thing that I need to mention so that you can see what this is. Okay, so suppose it looks like here I've only defined how the fundamental group acts on one particular point, x0 tilde. But if we change it to another element inside P inverse of x, like this one here, okay, we can do the same thing. We consider the same projection map, right? And the only thing we did was we changed the base point here, right? And then we can do the same sort of definition, and that gives you an action of the fundamental group on a different point inside that P inverse of x0. And we'll see an example of that later. Okay, so at the end of the day, I want to say that this defines actually a transitive action of the fundamental group, pi1 x0, on this inverse image of a point, that base point there. And of course, if you have a transitive action, we want to study what is its stabiliser. And its stabiliser, it will be some sort of subgroup of this fundamental group here. And what is that? Well, it turns out that there's a very nice, simple way to describe what that is. What we're going to do is we're going to look at the fundamental group upstairs. Okay, remember the fundamental group is a functor. And so you can look at the image of this fundamental group downstairs. So you look at the fundamental group upstairs, you look at the image downstairs. It's actually injection, as it turns out. And that image is actually the stabiliser of x0 tilde under this Galois action. So in particular, what it's going to tell you is that, of course, the orbit, which is the whole of P inverse of x0, is just the fundamental group modulo the stabiliser. So it's basically pi1 downstairs, okay, pi1 downstairs, modulo pi1 upstairs, because pi1 upstairs will map down like that. Okay? And one corollary that we'll see about, from here is that, remember we're assuming that x0 is connected. So this will actually show you that, and also x tilde is connected. Okay, so you can move this around, and as you move this around, you get something that's conjugate. And so, in fact, what you'll see is that this, the cardinality of this inverse image, what's called the fibre of this projection of this covering map, the cardinality of this is independent of that point downstairs, x0. Okay, and this is one way of measuring how many sheets you have. Okay, that's how many sheets that you have of this cover. So the degree of this cover is the cardinality of this fibre. Okay, so I don't want to go through the proof of this. It's quite involved, but I want to show you why it ought to be true. And I think if you see the picture, you really see that, oh, okay, it's not such a complicated thing at all. Okay, so the first thing that I want to do is I want to look more closely at the action and to see why is it that it actually gives an action. So in other words, if you multiply in the group, okay, in the fundamental group, okay, and let that product act, why is it the composite of two actions of the individual elements? Okay, so let's pick two elements inside the group. Okay, so maybe I'll pick an F downstairs here. Maybe the first one just wraps around twice in this direction. So once, twice. Okay, so that's the F that you have here. And what's the F tilde that you have here? You have to lift that. So you go lift it, and this is the unique lift, right? And you go around twice, and that's what you have. Okay, so there's your F tilde. And then here, this is F dot x0 tilde. And now let's suppose you have another group element in the fundamental group. And let's just do one loop that goes in that direction. So here's a G, and it just goes around once like that. So what you do now is instead of using this x0 tilde, you start with this point here. Okay, you're going to act on this. Okay. So you're going to get a G tilde, and it just goes around like this, once like that. That's G tilde. And so that's G acting on F, acting on x tilde, 0 tilde. Now, if you multiply these two loops, what do you get? You just go around, firstly, F, which is twice, and then G, which is a third time. And how do you let that act on this x0 tilde? Well, you have to lift that triple loop, okay? So that gives you first this one, and then this one. And where is the end point of this path? It's moved x0 tilde down to this one here, which is the same as this, okay? So that shows you that you have a transitive action, or an action at least. Okay, so the transitivity, yes. Let's have a look at transitivity. Why do you expect that to be true? Well, suppose you have 2 points in this fibre here, P inverse of x. Remember, this x tilde is going to be connected. So we just find a path from one to the other, like path from here to here, okay, or here to here. You take that path, and if you map this path down to x downstairs, of course, that's going to give you a loop whose lift is the original path that you have. So that means that you can use that path to move from any one element in the fibre to any other element in the fibre. And that gives you transitivity. Okay, and the final thing that I want to do is just comment on why you expect this to be the stabiliser. Okay, so it's quite easy at least to see why the image of this has to be contained inside the stabiliser. And actually, if you look at what that says, it's quite easy to see that yeah, it has to be the whole stabiliser. Okay, so let's firstly just pick something that's inside here, a loop that is inside here. Okay. Of course, in this particular example, it's a bit redundant because it turns out that in this, for R, okay, the fundamental group of R being contractible is going to be trivial. Okay, but let's just see the argument pictorially at least, which is quite easy. Okay, so we're just going to pick some sort of a loop here like this. So the only loop that you can sort of pick is going to be something like that. And we want to say that this loop, okay, firstly, it gives you a loop downstairs. And you want to say that the action of this loop on this point is trivial. It stabilizes this x0 tilde. And why is that true? Because if you take this loop, you go downstairs, how do you work out what its action is on x0 tilde? You lift it to a path upstairs, but that's the original loop that you have here. And since it's a loop, its endpoint is the same as the original x0 tilde. And so applying the image of this loop to this x0 tilde leaves it at x0 tilde. And it's quite easy to see that actually the whole stabilizer has to be all those elements of that form, almost by definition. And that gives you the key proposition, okay, and also ties in the fundamental group with Galois actions. Okay, so just to sum up, okay, given a fundamental group, this will define a transitive action on the fibre of the point, the distinguished point, the base point here, and the stabilizer of that is just the image of the fundamental group upstairs into the fundamental group downstairs. And so you can look at this fibre as a group, as a set with the operation of this fundamental group, and as a set, it's going to be this modulo this fundamental group here. I hope you enjoyed this adventure in pure mathematics.